Okay. Sure. So previously we had an introduction to Aspen. We looked at how to specify our components, how to choose a property method, how to run some analysis. And then we went to the simulation window. We had a very basic simulation to try out, just to introduce us to some of the things that are there. The next thing that we want to do is we want to learn how to use very specific blocks in Aspen or units in Aspen that can help us in simulating different processes. So for the one we did previously, we used a simplified reactor. We had a separator. We had a mixer here, a heater here, cooler there. But now we want to look at other um, units and other blocks like distillation columns, how we can use them for distillation processes, blocks for absorption, some of these things. So that's what we are really going to focus on for today. We are going to look at distillation columns for today. Okay. Okay. So I think we've spoken about that introduction already. Now we know that when it comes to distillation, we are talking about a kind of separation or a device that is used for separating a mixture, and the separation is done based on the difference in their relative volatilities. So you have maybe two components together. One has a volatility different from the other, and because of that difference, you can separate them. You apply some amount of energy, or you put in some amount of energy, and then one will become vapor, one remains as a liquid. Then we can do a separation, or one will have more of one in the vapor phase and more of one in the liquid phase, and then we can do our separation from there. And Aspen has different blocks that we can use for the distillation simulation. So we have all these blocks down, and the specific things that each of them do, it's detailed out in the first slide that I sent to us. So I'll send this one to us as well after today's discussion. But for today, we are going to focus on two of them, the DSTW and then the RADFRAC. So the DSTW is a simplified model. The RADFRAC is a more rigorous model. So for the DSTW, it's a shortcut model. We can just put in some initial data just to quickly get an idea of what to expect. But for the RADFRAC, it's a little bit more detailed. You can go into details with the column internals. You can specify so many different things over there, and it can account for even some kinetic relations and all these things. So DSCW is a shortcut method. RADFRAC is a more detailed and a more rigorous model that we can use. Okay. Now for the DSTW, we work with a single feed, and then we have two products. So we have our tops and then our bottom products, right? And it's using the Gilliland, the Win, and then the Underwood method for the shortcut calculations that we spoke about to help us determine the number of stages, the minimum reflux ratio, all these things. We are familiar with these things, right? You mentioned that most of you are in third year and final year. Please, are we here? Are
We
we
are
familiar
getting,
with these things? Please come again.
we are getting familiar with this.
Okay, okay. That's fine. Okay, right. So we have some of these um methods that we can use for some of these calculations. And for the DSCW, it's going to apply these things. Okay. Now, the advantage of working with these shortcut models or these shortcut blocks is that they can give us some initial or some very good estimates that we can use in the more rigorous models. So if you want to just do something quickly, get some quick results, you can work with your DSCW. Then you can transfer that data to a more rigorous block like the RADFRAC to get something that is a little bit more accurate or a little bit more specific in nature. So that's the advantage of some of these things. You can start with a shortcut model and then translate that information to the more rigorous one. Okay. So we want to look at how we can use the DSCW by looking at this example. So the question says that an equimolar mixture of benzene and toluene is to be separated by distillation to produce a distillate containing 90 mole percent benzene and a bottom product that contains 98% toluene. The distillation column is to operate at 1 atm pressure, and the feed to the column is a saturated liquid. Use the DSCW program and the NRTL model to estimate the minimum reflux ratio and the minimum number of stages to accomplish the separation. And then the second part is the actual number of stages and then the location of the feed stage if the column is operated at 1.2 times the minimum reflux ratio. So there's a lot of information here. We'll take it step by step. So the first thing that we would want to do when we come to Aspen is to choose our components. And from the question, we know that we are dealing with benzene and toluene. So we have two components that we are working with. So we'll start by specifying them. And remember, you can
Mr.
type,
Tip,
yes, please.
Please, I wanted to ask if the meeting is being recorded
Yes,
because
please, it is.
I don't think.
Yes, it's being
Oh,
recorded.
okay.
Okay.
Yes, please. Thank you.
As we mentioned the last time, if we want to specify a particular component, if it's a very common thing and the name can fit there, you can just type it
I
out
think that boy to go take good there.
and then Aspen would identify that, right? Or you can use the find feature. Please, is there a question? Okay. You can use the find feature to search for the specific thing you are looking for. So we've done all of these things before. Okay. Let me rename this. Right. Then the next thing we do from here is to specify a property method. So I'll click on next. And from the question, we're told to use NRTL. So I'll just click on next again, and then I can run it now. So now we have all of that down. Now, before we jump into the separation, realize that we are dealing with a distillation column. We are trying to separate two different compounds. And we know that there are some compounds that will form azeotropes, which will become, so they would have a certain point or let me say it this way, there will be a certain point we would get to where the separation becomes a bit impossible. We can't really do the separation, right? So I want someone to help us out. What do we mean by an azeotrope, or what's the azeotropic point? Anyone? I think the person who had been giving us feedback has dropped off the call, so another person would have to answer. Manasseh, are you there?
yeah, I'm around.
Okay, so can you help us out?
Um, is YouTube
Yes, anything you know
um,
about it,
a
anything you
mixture of
can say about
silicon, maybe the benzene and toluene, and their
it. Please come
boiling
again.
point, a mixture of silicon
Yeah.
which which have their boiling points coming close to each other, making it impossible to separate by maybe distillation.
Okay, so we know for azeotropes, yes, it's difficult to separate by distillation because as you heat it, as part of it is becoming vapor and we still have some being liquid, you realize that the compositions are not changing, right? So that's the main thing. The compositions are not changing, and so it means you can't do an effective separation. If you should condense the vapor, you're getting back the same thing you started with. You've not done any effective separation at the end of the day. Right. So that's the thing about azeotrope. So you don't want to waste energy with such systems because at the end of the day, you're not really going to do any separation. So we need to check to make sure we don't have any azeotropes. And we know how to go about this. We are dealing with a binary system. So we can come to our analysis tab like we did when we're looking at how we can perform some analysis on different systems. And we'll click on binary. We can generate a TXY diagram. So we don't really need to change much over here. The question said we are working at 1 ATM. So this is approximately 1 ATM. You can decide to change this to ATM and put the one there as well if you want to. But we will get fairly the same results, right? So we have benzene and toluene. We are doing it on a mole fraction basis. We are starting from 0 to 1, and we are just working with an interval, or the number of intervals we're working with are 50. So there's not really much to change over here. We can run the analysis and then we have our TXY diagram. So we realize that there are no azeotropic points in here. So we can easily do our separation if we have to. Now we want to, aside just checking that, we want to also know at what temperature are we going to be operating at, because we realize that the question didn't give us a temperature, right? But we're told that we are dealing with a saturated liquid. So at what temperature would we have to operate at? So we can come to results And then we can look for where we have our mole fraction to be 0.5 because we're told it was equimolar. And then we see that the temperature that we would need for it to be saturated at that point would be 92.0792 degrees Celsius. So that's the temperature that we are going to be using for our feed. Please, is that okay?
Yeah.
Okay, that's fine. So we'll be using 92.0792, approximately 92.08. So that's what we'll be working with. So now that we have,
So
yes,
yes.
please.
So we take the mole fraction of benzene at the midpoint forward. So 0.5.
Yes, so that's so remember the question mentioned that we have an equimolar mixture that we are feeding into our column to be separated. So if it's equimolar, then it
Oh,
means that the mole fraction is 0.5. And we want to know the temperature that it should come in at for it to be a saturated liquid. Also for it to be saturated. So we would need to find that temperature. And that's the value that we've gotten over there from Aspen,
okay.
the 92.0792.
Thank you.
Is that okay?
Yes, please.
Okay, sure. So now we can come to the simulation environment now, and then we can start out our simulation. So for this one, we'll come to columns. And can you see everything clearly? Okay. So we'll come to columns, and with the columns, we are going to pick our DSTW first. So we'll just place it down. Then we'll add our streams. So remember, where we see the red arrows, those streams are compulsory, right? So we'll add them, and then we can now specify the feed. So we always specify the feed and then the blocks. So the temperature we said we are using was 92.0792 or approximately 92.08. The pressure was 1 atm. And then the flow rate from the question, let's see. Okay, so we can use, um, let's use a basis of 100 kilomole per hour, right? So we can specify this to be 100 and it's equimolar. So for our mole fraction, it will be 0.5 for both of them. Okay, so that's for the material, the feed. So let me label this as feed. We'll use it again very soon. Then for the column itself, the question told us that we want to work with, or it said that we are operating at 1.2 times the minimum reflux ratio. So I'll say a few things here. When we come to the column specifications, realize that we have the option to specify the number of stages if we have an idea of them, or the reflux ratio. Right? But from the question, we are having a question in relation to the reflux ratio. And it said it should be 1.2 times the minimum reflux ratio. Now, if I should just put in a value of 1.2, I'm telling Aspen that the reflux ratio should be 1.2. But if I want Aspen to multiply the minimum reflux ratio by 1.2, then I have to make it negative 1.2. Please, I hope you are here. So once you put a negative in front of this, what Aspen is going to do is that whatever minimum reflux ratio you have, it will multiply it by that value, the 1.2. If we make it positive, Aspen is going to take it that we want the reflux ratio to be 1.2. Please, I hope you get the difference.
Yeah.
Please, is that fine?
Yes.
Okay, so whenever you see a negative in front of a value like this, it's just that Aspen is going to multiply the minimum reflux ratio by that value. So we'll see it even as we continue. And then for the pressure, the system was at 1 atm. We are going to work with the assumption that we are not really having significant pressure drops. So we'll keep the condenser and the reboiler pressure at 1 atm. Okay. And we are going to also consider the fact that when we have our separation, the vapor phase, we'll condense it back to form a liquid, right? So that's why we are keeping this here as total condenser. If we expect a vapor distillate, just a vapor distillate, we can check the second option. If we expect a mixture, it's some vapor, there's some liquid in there, you can check this last option here, then specify what the vapor fraction in the distillate should be. So we will keep it under total condenser for now. You can actually try out the partial condenser with everything being a vapor distillate as well. Now, the next important part we want to look at is this part over here, the key component recoveries. Realize that what we were giving from the question, we're told that the distillate should contain 90 more percent benzene, the bottle should contain 98 more percent toluene. So we have the composition there. But Aspen is asking us for the recovery, right? So how much of the feed are we having in the distillate? How much of the feed are we recovering in the bottom? That's what we are looking at. So the calculations were done in the slides. I'll show that to us quickly, and then I'll explain what is happening there. It's just a matter of material balance. Okay, I think we're talking about all of this. Yes. So we have our feed to be equal to 100 kilomole per hour. That should be equal to the distillate plus the bottom, the flow rates there, right? So this is our overall balance. Then we can do a balance for benzene. So we know that if maybe this is our column, we have our feed, then we have our distillates, and then we have our bottoms. So we can have the overall balance first, and then we can have a balance for benzene. So 0.5 was the mole fraction of benzene in the feed times the um, total flow rate over there, right? Should be equal to 0.9 because we're expecting 90% of it in the distillates. And then in the bottom, we're expecting 2% because toluene was 98% in the bottoms. So if we should do this, we have two equations. We can solve them simultaneously. We'll get the mole flow, the total mole flow for both the distillates and then the bottoms. But then as we said, we're looking at the recovery. So how much of the benzene from the feed came out in the distillate. So that's what we are doing over here. So in the distillate, this was the mole flow for the distillate, the total mole flow for the distillate. We said 90% was for benzene. So 0.9 times that to give us how much benzene is in the distillate, divided by how much benzene was in the feed, and that will give us the recovery. Please, we are familiar with these calculations, right? Please, do we get it, or is there any parts I would have to go over?
Yeah, we are okay. We are
Okay.
okay. The balance.
Okay, we have the recovery in the distillate, and then we have the recovery of toluene as well in the distillate. So notice that in Aspen, what we are specifying here, we're looking at the recoveries for just the distillate. Keep it in mind. So we see here light key. We are looking at the lightest thing we have, or if we have more than two, right, we would specify what our light key should be and what our heavy key should be. So here we have benzene, and then the recovery was 0.981. Let me see. Yes, it's 98. And then toluene still in the distillates, right? So we don't do distillates and bottom. We do everything for just the distillates. So toluene in the distillate was 0.109. So we specify toluene, and then the value was 0.109. Okay. So we can run it now, and then we can look at the results. It's taking some time to load, but it will come soon. Okay. Okay, so our results are available now, so we can check it out. So we can check the results of the streams, and we can check the results of the block. Let's check the block first. So we'll right click, and then we'll click on results. think just a minute, it will come soon. Okay. So now you notice that Aspen has gotten as the minimum reflux ratio. If you should multiply this by 1.2, you will get the actual reflux ratio. So 0.918203 times 1.2, and we'll get exactly this, right? If we had made the reflux ratio 1.2, positive 1.2, Aspen would have kept the actual reflux ratio as positive 1.2 or as 1.2, as I mentioned earlier. So let me just show that to us. If I should run this, realize that the actual will become 1.2. It would use the value that we have given it. Okay, I think it's slowing down a bit, but it will come. Realize that now the actual is 1.2. It's using the raw value we gave to it. So if you want the actual reflex ratio to be a multiple of the minimum, then we have to put the negative in front of it. So that's very, very important for us to keep in mind. Okay, so we'll put a negative back there. Now, we also know that we can try varying the number of stages, and then we can see the effect it would have on the reflux ratio. You know that there's a trade-off between them. If you have more stages, you don't need such a high reflux ratio to do the same separation. If you have less stages, you need a higher reflux ratio to do the same separation. Right? So there's a trade-off there. So what we want to do is that we want to generate a table that will show us that if I have maybe this number of stages, what reflux ratio do I need? Right. So still under the specification for the distillation column we just specified, we can click on calculation options. Then we can check the first one. So we want to generate a table of reflux ratio against the number of theoretical stages. Then we can put in our initial number of stages. So the example that we used in the slides was 8, right? So we can put in from 8 to maybe any value. So let's put in the minimum here was given as 6. So let's put in 8 here. And then let's end this, let's say somewhere 20 for the final number of stages, right? And we want to work with 11 values. So that's fine. So if we should run this, so our results are available. So how we can check the results? If you look at the simulation pane, this side over here, the far left, right? You see the blocks that we have. So the block we just placed down is B1. We didn't rename it. So we could have renamed it, but then over here it's B1. So I can come down and then come to the results. And I can come here to my reflux ratio profile. Or you can do what we did previously. You right click and click on results, right? Then we come to the reflux ratio profile. So we see that for every theoretical number of stages, we have the corresponding reflux ratio that we would use or that we should use to achieve the same separation that we are looking for. So this is another thing that you can also do with Aspen. Okay. Now the next thing we want to do is that we want to now try one of the rigorous models. Remember we mentioned that DSTW is a simplified model. So let me rename this as DSTWU. We said that if we are working with RADFRAC is more rigorous, it's more detailed, it requires more information, right? Or we can specify more um, details there. So what we are going to do is that we are going to place our RADFRAC block down, and then we'll connect the inlets and then the outlets. Now, one of the things I really like to do is that if I don't want to delete this block, right, but I still need to use the same feed, I don't want to re-specify the feed. So what I'll do is I'll just duplicate it so that it would affect both blocks. So the idea behind that is I can take this feed, pass it to a unit that will just copy the same thing, and I can send it to another block. So I'll disconnect this first. So I'll click on reconnect, and I'll disconnect it from where it is going to. So reconnect destination, and then I'll just place it down for now. Now, how do we duplicate the block? How do we copy it? So we'll click on manipulators, and then we'll click on duplicate. That's the second one we see here, the DUPL. That's duplicates. So I can place the duplicate block down, and then I can connect this into the duplicate block. So this is the stream I want to duplicate, or the stream I want to copy, right? So when we do that, we can now take the outlet from the duplicate and send it to both columns so that we don't have to delete one. So I can take this and then connect it to my DSCWU. And I can take that and then connect it to my radfrac. Please, I hope you are here up to this point. Is that we all here up to this point?
Mm, mm,
Okay. Now the next thing is to connect the outlets. So for the bottoms, it's straightforward. But when it comes to the tops, you realize that we see two red arrows. If we should choose the lower one, then it means we are considering our distillate to be a liquid, right? So we are looking at a liquid distillate. We are expecting it to be condensed to form a liquid. If we choose the one at the top, we're expecting a vapor distillate, right? So we're expecting our distillate to come out as a vapor. It wouldn't be condensed. So because we chose total condenser for the DSCWU, we'll do the same thing here. So we'll choose the lower one for liquid distillate. If you are not sure, you can just hover your cursor over it and it will tell you what exactly it is. If you should choose the wrong thing, or if you should choose something and specify something else in your block, you would have errors. So I'll show us what I mean by that. So let's go into the radfrac itself, and then we can start the specifications. So let me label this as radfrac. Okay. So now we can double click on the radfrac and then we can start the specifications. Now, so this is what we are going to see. The first thing we need is the number of stages. So once again, the DSCW give us some results that we can use to start working with the radfrac. So we'll go back to the DSCW results. And if we check it, how many stages were mentioned to us? So, oh, let me come back here. So the number of stages, not the minimum, but then the actual, it was 15.5, right? So it means we'll have to round it up to the nearest whole number. So we'll use 16 because you can't have zero point 0.5 stages. You have to use 16 stages. So we'll come here and then we'll put in 16 for the number of stages. Now you notice that under condenser, if you check the options that are there, we have total, partial vapor, liquid, none. And remember, we placed it at the part that was supposed to be a liquid distillate. So if I should choose partial vapor, Aspen will give me a warning, right? So that's why I mentioned that it's important that you place your stream at the correct place. So if I'm dealing with a liquid distillate, then I'm supposed to select total condenser. It's supposed to condense what I have, or it's supposed to condense my distillate to a liquid. So then we have that now. It's going to be total, a total condenser. You can play around with the kind of reboiler you want to use, the valid phases that your column is dealing with, and then the convergence. For questions like this, for very um conventional processes, it would usually be standard. But if you have cases where you have very strong non-ideal liquids, you can choose that. Or if you are dealing with maybe petroleum um components or some things that have very wide boiling points, you can choose that option as well, right? So these are some of the things that you would come across as you try different examples. Now, the distillate rate, we calculated that from the question. So the distillate rate was 54.5 kilomole per hour. So we'll just put that value in here, the 54.5. And then the reflux ratio, we'll take what we got from the DSTW. So for the DSCW results, we had the reflux to be 1.10184. So I'll just copy that and then I'll paste it here. So we have that now. Now, someone may decide that, okay, I don't want to specify the reflux ratio. You can choose other things. Maybe you want to specify the reflux rate. So not the ratio, but then the rates, you know, the flow rate or the boiler up rate or the boiler up ratio or your condenser duty or your reboiler duty. If you have information on any of these things, you can put that information in here and Aspen will be able to work with it. So now we are done with the first part. The second part is the streams, right? So we'll click on streams. And remember, if you see the red and white mark, it means something hasn't been specified. If it becomes the blue check mark, it means everything has been done correctly. So something is specified or there's an error somewhere. Okay. So we can come to streams. Now, S5, that's our inlet stream. We want to know the feed stage. That's the feed, right? So we want to know the feed stage, where it's going to come in at. So if we come back to the DSCW results, so you can see why the DSCW is very important. It gives us these pieces of information that are required. So the feed stage is 6.4, right? So if we should round that, we'll be getting 7 as our feed stage. So I'll come back to the RAD frac and I'll put in the value of 7. So you may consider um, maybe our feed is coming in above the stage, on the stage, or it's coming to our stage as vapor or to our stage as liquid. So these are different things we can do, right? And Aspen counts the stages from top to bottom. Yes, it's from top to bottom. So stage one is at the very top where we have the distillates, and then the last stage would be where we have the bottoms. Okay, so we are done with the streams. We can now come to the pressure. Since we are keeping the pressure constant in our system, we'll use the same pressure we've been using all along. So we'll click on pressure, and then we'll specify 1 atm just for the first part. The rest of them are optional. So if you want to specify the pressure for stage 2, you want to specify the pressure for the rest of the column, you can do that as well if you have that data. But then we are just working with the condenser pressure at 1 atm. So we'll specify just the condenser pressure. And you notice that it said stage 1 or condenser because, as I said, stage 1 is at the top. They count it from top to bottom. So where we have the condenser, where we have a distillate stream is stage 1. And then the very last stream is what we have at the bottoms, where we have probably our reboiler. So now that we have all of this specified, let's come back and then let's run the simulation. So all the simulation is running. Okay, I think our results are available now. Sure. So we can check the results of the RAD tracker as well. So we can right click and click on results. So all that is taking time to load. Are there any questions on what we've done so far?
Hello.
Yes, please.
Means you can use all the values you've gotten to result from the DSPW
Please come
into
again.
the results you've gotten from your DSPW.
Yes, yes.
You can use some of those values as your input for your rank track.
Yes, you can. Yes, you can.
Oh,
You can. So the DSCW helps you know where to start from to achieve your separation. Sometimes you may need to vary it just slightly, the values just slightly, or tweak some things here and there to get the exact separation you're looking for. But then usually the values will be very, very close to each other.
oh,
So we can even, in fact,
oh,
let's do that first. Let's compare the DSCW stream results and then the RADFRAC stream results, and let's see if there's a significant difference before we look at the blocks themselves, right? So um they have the same feed. So let me do it this way. I think it's better if I label them so that we don't get confused. I'm coming just a minute. So I'll make this one T1. The laptop is trying to slow down. And I'll make this one B1. So T1 is the tops for the DSCW. So top one. And then B1 is the bottoms for the DSCW. Then T2 will be the tops for the RAD frac. So T2. Oh, sorry. T2. And then the bottoms for the RAD frac will be B2. So we'll not really see
okay.
such a significant difference. But you might see something maybe in the decimal the decimal points, something slight. You may see more significant differences if you should specify the column internals. It may change things slightly, right? So that's another thing to consider. So I'll show us how we can do that, but that wouldn't be the focus for today's discussion. But I'll just show you where you can go, and then in subsequent discussions we'll look at that. So they have the same feed. So I'll just include B2 and then T2. Then we can compare everything. So S4 is the feed. And then I'll add T2 to it. So if we even check the temperatures, compare the temperature of B2 and B1. This is 109.72. This is 109.64. It's not so far, right? T1 and T2,
Yeah,
82.16, 82.19. Now let's look at the mole flows. So if we look at the mole flows, we see that we are getting the kind of separation we are looking for, right? Because we specified the distillate rate for the RADFRAC, and we were able to use that calculation in the DSCW. So we'll get the same thing. So now let's compare the value. So this is B1, benzene coming from the DSCW at the top. This is benzene coming from the RADFRAC at the top. So we see that it's just slightly different. This is 0.95, this is 1.0, right? Then if we look at benzene coming from, oh, sorry, that's the bottoms. B is the bottoms. Sorry. If you look at benzene coming from
bottom.
the tops for DSCW and then the tops for the RADFRAC, we see that it's also not so far off, right? There are just some slight differences because of the different equations that are being used. But if you should now include things like your column internals, the differences might become a little bit more significant. So for that one, if you are in the RADFRAC block, under the configuration, you can come down here. You would see design and specify column internal. So if you should click on that, you can specify things like your column diameter, the wear heights, all these things. So you click on that, you click on generate. It will generate some data for you, hydraulic data for you. Then you can now go into details with that. So I'll just show us how it looks like, and then we'll move on to um the other things that we were talking about. But I hope you see the difference. The
Yeah,
values are
the
quite
values are.
yeah. Okay. Sorry. This may take some time to load, but I think we can just wait a bit, it will come soon. So the other thing I was going to say was that if you check the results for the RADFRAC, just like we check the results for the DSCW, you right click and click on results. You get information on things like the reboiler duty, condenser duty, all those things are there, right? But then the advantage with the RADFRAC is you can now get the profiles. Okay. So you can get the profiles, maybe the temperature profile in the column, the concentration profile. This is where we specify the column internals. So we see a little schematic here. It starts from 2 at the top because the condenser is taken as 1, right? And then it ends at 15 because the reboiler is taken as the last one. Remember, we made it 16, so the reboiler is the last one. And then our feed stage is the 7. So we can now come here and then choose. We can even decide to make it a packed column. So we can choose the kind of packing, the start and end stage for the packing. You can specify the type of um internals that you are dealing with, the materials they are made of, the diameter, all these things. And you can even go further. So this is not even just the only template or the only interface. You can even go further and do a lot more with it. So I think for this particular one, we'll make time to talk about just that, right? But then for today, we just want to introduce DSCW and then the RADFRAC. And then subsequently, we'll look at this as well. So let me delete the internals we just did. Otherwise, Aspen will not allow me to continue. Oh, come just a minute. Sorry, my laptop is being stubborn. I'm coming. But I hope you get all the things I've been trying to say.
Yeah,
Yes, please. Yes, please.
Well, thank you for your questions too. So let's delete it from here. Oh, just a minute. Oh, surprised I'm not getting the option to delete it. And I've not even specified. Okay, I'm coming. Shouldn't be that way. I'm trying to delete the internal so that we can continue. Otherwise, Aspen won't let us run anything else. But I think before we even did this, we had already run the simulation. So we can retrieve the previous results that we had. So if this thing doesn't still work, we'll just move on. Okay. So let's move on. But you can delete the internals you specified. So if you should right click, you should be able to delete those internals. Okay, the option is not being available, but that's fine. So we can right click on the rat frag. I think we did that earlier. That's over here. Oh, still ask for data. Okay. Right. So we see the temperature, the condenser, the heat duty. We see all of these things. Right. So we can get reflux ratio. We can get the, oh, we specify the reflux ratio. Sorry. We can get the reflux rate. Right. For the bottom, we can get the boil up ratio, the bottom rate, all those things. Right. So we have all these um data available to us. So we can check all these things out, the balance, the split fractions. This will give us the material balance in our system. I mean, it's taking quite some time. I'll quickly move through this and then I'll show us how to get the profiles. Okay, so we have the balance, we have the material balance, the energy balance, what is coming in, what is coming out. You can check the split fractions as well. Now, if we want to look at the profiles, we'll locate the radfrag block. So that's over here. And then we would see, should see profiles. So we see profiles down here, right? So right under the radfrag um units, we can see profiles over here. So we can click on profiles. I feel like the columns thing we did is going to affect it, but let's see. If it affects it, I'll try again to delete it. Hmm. Yeah, it's going to affect it. Okay, so we see the profile, or we can see information about what happens at every stage. So for stage one, that's the temperature. For stage two, that's the temperature. It keeps going on like that. So the last stage can also get the pressure. But we kept it as a constant pressure, so we don't expect any pressure drop. You can get the heat duty, the liquid mole flow, the vapor mole flow. All these things are available to us. Now, maybe you want to see it in a graphical way. So we can come up here where we see plots and we can click on temperature. There's one for concentration as well. So we can click on temperature. Let's give it just a little bit of time. And then we can get the temperature profile. This looks interesting. So we can get the temperature profile, right? Or we can also work with maybe the concentration profile as well. So maybe we want to work with the concentration profile instead. So I'll come back to my radfrac profiles. Then I'll click this drop down here so I can see the other things available. So we have composition, we have pressure. You can check pressure as well, right? You can check all those other things that are available to us, flow ratio and all of that. So for the concentration, we'll go to composition. Okay. And we can choose what phase we are interested in observing. So if it's the liquid phase, we can choose that. If it's vapor, we can choose that. If it's both, we can check both of them. Right? So you can decide to check both of them. But let's leave it as just for just one of them so that the system doesn't slow down too much. So let's just leave it on vapor, and then we can look at what happens for maybe both benzene and toluene on a mole basis. So if I should click on OK, it will generate the plots for me. So I'll see the composition, the concentration profile for the liquid phase, right, throughout the system. So at stage one, this is the liquid mole fraction we're expecting for benzene. That is what we're expecting for toluene. We have the legend here to direct us. At stage nine, the blue one, that's the liquid mole fraction for benzene. That's the liquid mole fraction for toluene, right? So these are some of the things we can do. If you had multiple components, more than two components, you would really be able to appreciate these things even more. So you see the concentration profiles for all the different components that you have available. So we'll end here for now. Please, are there any questions? Are there any questions? Please, any?
No, please.
Okay, that's fine. So if there are no questions, then I think we can end here for now. So I would get rid of the column intern out thing. I'll save the document and I'll send it to all of us. Okay. So I think next week, okay. So this is it. So I can delete it from here. Okay, that's good. So it should be gone now. So I would save it, I'll send it to us so that we can all try it out. We can, I mean, use it as a reference. And then next week we'll move on to absorption, extraction, and then from there we'll try out our first assignments, and then we should be ready for the next stages. So thank you for your time.
Thank you.
Thank you, Mr. Otiepin.
Okay, you're welcome.